Hello and welcome. My name is Bilal Rafiq, and today is Elastomer Draft Day. LSR versus TPE, what's the best pick for you? Today's video is sponsored by SIMTEC Silicone Parts, your LSR manufacturing partner. With co-designing, lab testing, prototyping, and mass manufacturing capabilities, SIMTEC is an ideal partner for your high-demand LSR projects. Today's topic is going to cover a contending matchup between two elastomers battling it out in the industry. Although they have their own unique characteristics, they also overlap on several other items. Today, we'll look at them both head to head. First off, we'll look at them individually and their overall background. Then we'll compare them side by side in a scouting report. Then we'll draft them for specific applications, looking at what's the best for each of those. We'll conclude with some forms of recommendation on what to do when you're selecting your elastomers for your projects. So, let's get started. TPE stands for thermoplastic elastomer, and as the name gives it away, it's a combination of hard plastics and soft rubbers. It comes via a pellet form and then is melted and then injection molded almost exactly to what traditional plastic injection molding techniques are. It can actually also be thermoformed or blow molded. It comes in a wide selection of options for different industry-specific requirements. So whether it be food contact, automotive, medical, consumer, or industrial, there are different options to select for that can meet those industry-specific requirements. There are also specialty grades that have special characteristics, such as electrically conductive, flame resistant, heat resistant, fiber reinforced, and tear resistant that you can select from. There are also bondable grades that can be adhered to different types of plastics, whether it be commodity or engineering plastics, and also certain types of metals. Looking at the TPE family and starting from first the polymer base, there's two distinct branches it breaks off into. One being the thermosets, where LSR resides, and the other being thermoplastics. However, you can see that TPEs are a combination of thermoplastics and elastomers, hence the name. But under that family, there is a plethora of different combinations of the plastics and elastomers. Some can contain polyethers, copolyesters, polyurethanes, polyolefins, and this one is interesting, a TPV, which is a cross-linked or vulcanized thermoplastic elastomer. So it's sort of like a combination or hybrid between a TPE and a thermoset material. Now let's look at the background for LSR. LSR stands for liquid silicone rubber. It is an HTV thermoset elastomer, or high temperature vulcanized. You need the cavities to be very hot for the silicone to fully cure and cross-link. It's a blend of different polymers, however, majority of it is made of siloxane. Siloxane is a combination of silicon and oxygen repeating over and over again. It comes in a liquid form, both A and B component, one containing the platinum catalyst, the other containing the crosslinker and the inhibitor. And it's pumped in to the injection molding machine and mixed over there, also with a third stream, typically adding pigments. And then it's maintained at a room temperature to ensure that it doesn't prematurely cure within the dosing system and the cold deck, finally curing it at a minimum typically of 130 degrees Celsius to begin its curing and cross-linking action. It has a very strong intermolecular bond, so comparative to other elastomers, it's more chemically and mechanically robust. It's naturally inert since its chemical backbone is inorganic, so it does not react with biological material, and it's hypoallergenic. There are also specialty grades available, whether it be oil-eluting, flame-resistant, self-adhesive, tear-resistant, low coefficient of friction, and many, many more. The self-bonding one to mention can adhere to certain types of plastics, and we'll go over that list later on. and it can also adhere to metals. Looking at the silicone family in general, it's two distinct breakdowns, one being the high temperature vulcanization and the other being the room temperature vulcanization. Starting off with the HTV, the breakdown goes into HCR first. And so it can come in two different curing options, one being a peroxide cure or an addition cure, with one of the options being platinum catalyst. On the right-hand side, you will see is liquid silicone rubber, which typically comes in a platinum catalyst. And in the middle, you will see fluorosilicone, which can have both a HCR or LSR option. And fluorosilicone allows it to be more robust against harsh chemicals or oils and gases. On the other side, we have the RTVs. And so as the name gives it away, it allows it to cure at the room temperature. And it comes in a one component or two component option, either being condensation cured or similarly being platinum cured. Now let's look at the scouting report and compare them to, first looking at their properties. Let's start off by comparing the service temperature range. This is a range of temperatures where the materials can withstand without degrading mechanically or chemically. LSR and TPE match up quite well at the low end. However, LSR is able to achieve 250 degrees Celsius or 480 degrees Fahrenheit at the high end, whereas TPE is limited typically to 180 degrees Celsius or 350 degrees Fahrenheit. When it comes to compression set, which gives you an understanding of how well the material will perform in a sealing application, especially during high heat or harsh conditions, the material is tested by compressing it to a certain thickness or a certain percentage and is then put in an oven or some other accelerated environment where it's then taken out, then released, and then measured to see how much it returned to its original state. So for this, the lower the percentage, the better. For LSR, it typically can go under 20%, and it can withstand the harsh heat applications and maintain that under 20% quite well. Certain specialty grades can even go under 10%. For TPE and those specialty grades for TPE, they can go under 30%. And it can only do this for a lower temperature range as we described above in the service temperature range. And it can only do it for short durations. Typically, TPE can go even above that to 60% or more. When it comes to flammability resistance, both LSR and TPE are able to achieve ULV0. However, LSR is naturally going to be less flammable because of its chemical makeup, whereas TPE is naturally more flammable as it is crude oil based. When it comes to the medical certifications needed for the medical industry, and these two ISO 10993 and USP Class 6, and testing for biocompatibility and cytotoxicity, LSR is naturally going to pass these every single time because it has an inorganic backbone, whereas TPE will have a limited selection to pass those requirements. When it comes to odor, taste, and leachables, LSR relatively has very low. The only thing that it has is these low molecular weight siloxane chains, which are often also called volatiles, and they're driven out via a post-curing process. And also LSR can achieve reach and ROHS quite easily. For TPE, it can also meet those requirements and have low odor, low taste, and low leachables. However, often they contain plasticizers, phenols, or various unwanted additives. When it comes to additive ability, LSR's materials are typically always set, and they're off the shelf. So you just purchase them, you bring them to your facility, and then you mix them and process them. However, the only thing we do add to LSR is the pigments via third stream. And in rare cases, we add other additives to give special characteristics. For TPE, as we saw before, there is a wide family and a wide selection of different combinations that you can have to achieve certain special characteristics. When it comes to dimensional stability, LSR has a low temperature influence on its dimensional and volume in size, because it is fully cross-linked, so it has little to no creep. Whereas TPE is heavily influenced by the heat and changes its dimensions quite rapidly, because it has no cross-linking, unless you go for the TPV material. Now let's compare them both from a processing standpoint. Let's first begin by comparing the capital investment needed for these two materials. For LSR, it's going to be slightly more expensive than TPE. This is because of the added amount of precision and accuracy needed between the mold plates. Because LSR's viscosity is so low, they say it flows like water in comparison to TPE, it can flash very easily. Also, it's important you maintain the cold deck at room temperature to ensure that the LSR does not prematurely cure. In addition, the cavities need to be distributed very evenly when it comes to thermal balance to ensure that the LSR is cured evenly through and that it's rapidly cured. For TPE, you can follow a typical plastic molding perspective, so the mold costs are typically going to be lower. And this is when you're comparing the same cavitation size and also the same geometry. When it comes to high volume requirements and output, LSR's low viscosity allows you to build very complex runner decks with direct injecting capabilities. For an example here that I have a single wire seal for automotive connectors, we can go up to 256 cavities. And for two shots, we can go up to 96 plus 96 cavities. For TPE, you often want to keep the molds much smaller so you can control the hot runner system. So you would need added molds to lead up and sustain the same output as an LSR mold. For the overall output, LSR needs cross-linking, so there is an added amount of time. So cycle times for LSR versus TPE, LSR will be slightly on the higher side. For TPE, excluding the TPV, it's typically going to have a faster cycle time as you just need to cool down the material with no cross-linking. For the demolding process, LSR is a little more delicate and you want to ensure you do not damage the component as you're either pushing it or grabbing it. So you want to make sure your demolding process is a little bit slower to ensure the integrity of the component. Also, ejector pins are not traditionally used for LSR as it's a risk for flash concern. Where TPE, you can still use ejector pins and the material is more forgiving, or it maintains itself quite well, so you can eject it out much quicker. When it comes to two-shot material selections, both of them have opportunities to bond to either plastic or metals. However, LSR is more limited in that scope. Traditionally, we use PBT, nylon polycarbonates, and certain metals like stainless steel or aluminum. However, we need self-adhesive promoters within the material to bind to those substrates. And also, those substrates need to have a high enough heat deflection temperature, typically above 140 degrees Celsius or 280 degrees Fahrenheit, to ensure it does not warp or get damage in that LSR cavity. For TPE, you have a wider selection of substrates and plastics you can choose from because TPE is thermoplastic based. And you can also bond to those commodity plastics like polypropylenes and polyethylenes, making it more ideal for consumer products and single-use applications. For part complexity, since they're both elastomers, they're more forgiving in the amount of undercuts and rib geometries that you can have. However, with LSR, you can even go more extreme because of the ability to go lower on the durometer scale. And we'll look at these side by side on the slide next. Slides are possible for LSR and TPE. However, LSR is more of a concern because of its low viscosity. It can flash very easily. When it comes to the secondary processes to finish off the components after it's been molded, LSR sometimes needs to be post-cured. And this is when it's going into a food contact application, mother-child care, and certain medical products. This is to drive out all the volatiles or uncured LSR to make sure that these do not leak out and they meet certain industry requirements. For TPE, post-curing is almost not needed. However, it may be needed for those TPV materials that still has cross-linking. When it comes to the durometer ranges, LSR is traditionally scaled on a shore A. And as a reference, you can see that jelly bears are 10 shore A. And the scale often goes for silicone from on the lower end to 1, all the way up to 90. For TPE, you can see it overstretches on that shore A scale, and it's limited on how low it can go, to roughly 35 to 40 shore A. Here I have an example to show you the extreme ability of LSR on the lower side. This is a two-shot component combining PBT and a self-adhesive LSR that is rated for food-grade applications. The thickness of this membrane is 0.1 millimeters in thickness. And this component acts as a balloon. So it's filled with liquids and fit inside of a cup used for the elderly community. And since you don't have to tilt the cup back too much in order for it to compress and push the liquid out. This makes it ideal so there's not too much stress on your neck or any other joints as you're trying to drink your favorite beverage. All right, we made it now to the draft. Let's begin selecting these two materials for different applications to see where they best fit. Let's jump into our first draft choice. So first, we want to go over an application for a smoke and CO2 detector cover. Previously, the customer was purchasing two components. One was the elastomer seal and one was the polycarbonate cover. The problem here was that when the technician would come by and remove the cover from the module, the seal would get out of the profile, and as the seal was being replaced, it would not be replaced to its original profile and cause small gaps, and therefore there was leaking where it compromised the internal components. As you can see from the cover here, it's quite large, and it has a very intricate profile that starts here, comes around here, and goes around and follows the outside till it comes all the way back. So this was a continued problem as the part was in use. Now, we identified three main attributes that we're looking for out of the elastomer and the plastic cover combination, as the polycarbonate they were using wasn't necessarily the perfect fit for a two-shot application where we could overmold the plastic cover with silicone inside of the same mold in two different halves. So as I mentioned before, plastic needs to withstand the high heats of the LSR side, and polycarbonate traditionally is below that threshold. So we had to select the right one having the particular attributes. But for the elastomer, we needed the compression set to be at least under 30% and withstand durations of at least 5 years or more. We wanted to be stable and maintain its mechanical and chemical stability over the temperature ranges of -32 to 93 degrees Celsius or -25 to 200 degrees Fahrenheit. And lastly, we wanted to bond the polycarbonate. Specifically, the polycarbonate needed to be very transparent, and it needed to withstand any UV yellowing reactions that could happen over the lifetime. So we need to have UV stabilizers. So looking at both options, it was selected based on two main points that LSR was the best choice. The reasons is that LSR has superb compression set, which again translates into its sealing performance. So with silicone having less than 20% and withstanding over the given temperatures and over the lifetime needed, LSR was the best choice for that reason. And also, it bonds very well to polycarbonate and can maintain that bond over the lifetime. As the technician is removing it and replacing it over and over again, there may be a lot of stretching going on between the LSR and the polycarbonate housing. So it's important to maintain that bond so that there's not similar issues that they had before. So LSR again is the right choice for this application. On to the next one. We have a disposable razor handle with a soft rubber grip. The reason for the soft rubber grip is to ensure that the user can hold on to the razor as they're using it in the shower or over the sink, as the water can make it very slippery. So the main reasons or the main attributes we're looking for here from the elastomer, one was the resistance to moisture. So we want it to be hydrophobic, and we also didn't want the elastomer to soak in that water. We want it to have a soft feel, but also to be frictional so that when it does get wet, the user can hold on to it. We want it to either be overmolded, so it could be cost effective and easier to reduce any assembly, but if there was the assembly needed, it could easily fit and snap in to the handle, especially if it's a different material like this one being metal. And lastly, and most importantly, is it needs to be cost effective, as this is a very cost sensitive application. So looking at the two choices, we determined that TPE is the best choice. So not only does both of them can have that tactile grip and be able to resist, however, TPE is a little bit better for abrasion resistance. So if there was nails or other abrasiveness done to the elastomer, the TPE will withstand that better than the LSR. And lastly, it's the TPE is going to have more cost-effective options. LSR is considered more on the premium side, and there are some less costly resin silicones. However, they come in with different attributes as well and different curing additive materials. So they could have different behaviors and different leachables in the material. However, TPE has some very good options that are cleaner for user interaction, and so that makes it more cost effective for this application. All right, let's move on to the next draft pick. Here we have an application for a gas regulator diaphragm. These are located very sporadically across all your gas run appliances, such as your stovetops, your gas water heater, and even your fireplace. The point of this diaphragm is to make sure that the natural gas is coming in at a certain amount, and also to make sure that it's activated and deactivated in case of any emergency situations. So we outlined three main needs for this application. One is that the elastomer needs to be very sensitive to changes. So it needs to be very responsive when it's activated. Another is that it needs to have a very low compression set. As you can see the diaphragm in my hand, the outside of this is a sealing rib, which encloses itself onto the housing. And then lastly, but also very important, is to have a very low hysteresis loss. So this is the regulator side, and this is the pressure sensing side. But the regulator can change very rapidly over time and in use. And so it's important that while it's in use, that the energy that's input into it is not turned over into frictional or heat energy, and it's not lost, that it's rebounds or goes back into physical energy. And that's what it means to have a low hysteresis loss. So considering those needs and looking at the two elastomers, LSR is the most ideal choice here. And let's go over why. So as I show you in the diaphragm, it's got a very thin profile. And so for the durometer selected and the response needed, the diaphragm is actually 0.2 millimeters in thickness, or around 0.008 of an inch. And this is very hard to do with a higher viscosity material. And so LSR was the only material that could achieve that thinness. It also needed to have a very low compression set over a wide set of temperatures. So your water heater, your fireplace, or your gas stove may be in some conditions that may be very cold or very hot. And so that seal needs to be maintained as the temperatures are ranging and moving quickly. And then lastly, the sensitive to physical inputs. Now, TPE could also achieve this quite well. However, LSR rebounds very nicely for certain durometers. So when I stretch it out and I let go, it comes back very quickly, which means it has a very good rebound resilience. All right, let's go to the next one. Here we have a phone case cover. Now, some phone cases may be just aesthetic. However, I think most of the ones that we use, we wanted to have an actual durability against it to resist any impacts. So some of the phone cases you might have might come in two different pieces, one being the rigid and plastic part usually, and the other being the elastomer or energy absorbing part that usually goes around the entire component. So we outlined some needs here from the customer. One is that it needs to be able to withstand the impacts that it will go through and absorb those impacts. It needs to be resistant to dirt and other cleaners. As we are using a lot of hand sanitizers, we want to make sure that the elastomer doesn't degrade. We want it to have a soft feel and be hyperallergenic as you're holding these phones for long periods of time in your hand. We just want to make sure it doesn't react adversely to the user. We want it to have a full range of different color options. And lastly, we wanted to have it to be electrically insulative, just in case there's a short circuit. We don't want that to go to the user. So looking at both options, we selected TPE as being the best draft choice. One is that it's very cost effective when you have short product life cycles. So with a new cell phone coming out every year and the design changing, the cases become obsolete, and so we need to retool and remake another different mold set to accommodate that new design. So TPE can adjust and be very cost effective to the nature of small or short product life cycles. And another important thing to note is that TPE is very good at impact absorbance. So I mentioned on the previous application that LSR likes to transfer the energy, especially on the higher durometers, but on the lower durometers, it can absorb the energy. However, on the lower durometer of silicone, it becomes very tacky and it allows a lot of dirt to stick to it. Whereas TPE naturally can be very tough and it can absorb when there's impact, especially on the corners here, instead of transferring it over and having your phone bounce around as it hits the ground, making several impacts. All right, let's move on to the next pick. For this application, we'll be drafting for is a wiring harness seals and gaskets. These are for the automotive connector seals that are located underneath your engine hood or throughout your vehicle. It's very important that we maintain these criteria when we're selecting the elastomer. One is the low compression set. So this is very important as the seals will go under very harsh conditions in high heat cycling for long durations. And also there'll be harsh weathering conditions as well, either in the colder or hotter desert climates. It needs to pass a wire insertion test. So when these components are all assembled together, you take one of these wire seals and you insert it inside of this mat seal. And as it's being inserted, it needs to make sure that it doesn't tear or rip. It needs to be electrically insulating and it needs to be cost effective. So we need to aim for a higher cavitation tool. And lastly, but also very important, is to have a multitude of different pigment options. This is important for their polka yoke setup, so they can easily assemble a multitude of different wires in the same assembly line without confusing each of them, because they can look very similar to each other and have very subtle differences. So weighing the two options we have here, LSR is the ideal choice, and this for the following. The compression set is the best between the two elastomers, so it can achieve the under 20%, and it can do this for long durations of high heat exposure. We can build a very high cavitation tool. So for this one I mentioned earlier is 256 cavities, and we are able to be very cost effective when we can build those size tools. And lastly, it passes the wire insertion test. Not a lot of elastomers can elongate to the same extent without passing their yield strength and being damaged. All right, let's talk about the next one here. Electric shaver housing. These shaver housings are often used in very wet or, say, careless manner. They can be exposed to water and they can actually be submerged at times too, or just be rinsed over the sink. So one of the main importance is to have a very intricate seal, as these housings can be very tight in nature. So we want to make sure that the seal is small enough so that it could fit in the specific profiles that they need. So it also needs to have an ability to fill in very thin areas. So the material itself needs to be very low viscosity as is being injection molded. And lastly, it needs to have a very good compression set, so over 5+ years. However, there's no harsh conditions to consider, but it needs to have that compression set over the long duration. So looking at the two materials, LSR is the best draft choice. The compression set is the key thing here because it's going to be submerged. It needs to pass IP ratings and needs to have a very robust seal over the lifetime of the product. And lastly, it also bonds to PC and fills it very nicely in these intricate patterns. So it bonds very, very exceptionally well, more so than other elastomers to PBT because of its self-adhesive promoters inside of the LSR. Now let's draft the material for the fitness wristbands. These fitness wristbands can come in all shapes and sizes and are becoming more and more utilized today. The needs here are specifically for skin contact and soft feel to make sure that the user doesn't have any reactions as they're using this daily almost all the time. We want to have the ability to switch over to different colors and specific Pantone colors. And we also, most importantly, want it to be cost effective. So looking at the two options we have, TPE is the ideal choice to be drafted. Not only is there options to be hypoallergenic, but it's very cost effective for smaller or shorter product life cycles. So the need to retool and update to a next version can be done rapidly and more cost effectively. Next, we'll draft a material for surgical pumping diaphragms. There are key things to consider when you're looking at pumping fluids. One is to consider is it's a medical application. So if it's a medical application, we want to consider the two certifications we mentioned earlier, which is ISO 10993 and USP Class 6. Both deal with biocompatibility and cytotoxicity, making sure that it does not interact or cause adverse reactions to biological material. The next great importance is to make sure that it has exceptional rebound resilience. So as it's being pumped and pushed down repetitively, it's important that the material transfers that energy and doesn't change that energy into heat, but transfer it back into physical energy, and that it can do this very repetitively without being fatigued. And also, the most importantly is to have very tight tolerances. This component is very specific that mounts onto another housing component. So it's very important that they align consistently over the lifetime of the program. So looking at the both options, we have the best choice is LSR. The reason being is its mechanical characteristics in pumping performance. So LSR is almost always going to outperform other elastomers when it comes to dynamic, fast cycling pumping situations. And lastly, although TPE and LSR can both be comparable in their dimensional stability as they're being molded, LSR is going to edge out and have just a slight advantage over the lifetime of the project. That concludes our draft picks for today. Before we leave you, we want to give you some words of advice as you're selecting each elastomer or while you're selecting your supplier. So when you're looking at these two materials, you want to look at your performance you need from your application. Is it more weighted on strength or is it more of an aesthetic piece? Do you need a better compression set, better tear strength, or improved abrasion resistance? These are the things you want to consider as there are key differences between the two materials. What type of climate conditions will the materials be in? Is it going to be high heat for long durations or at a colder temperature? What type of chemicals will be exposed to the material? Is this a franchise or short-term solution? So are you looking for a supplier to supplement some components quickly to test the market? Or do you want a long-term solution for a supplier to deliver consistently over a 10-year project? What is the salary cap? Are you willing to invest a lot up front and then have a lower piece price over and cost over the lifetime of the project? Or are you looking at it a little bit differently? When is the starting date? Do you have to meet the product release date of a corresponding component on the market? Has to deal with the phone cases or the fitness wristbands. Is it a short product life cycle? Do you have to end the product life in about 1 to 2 year time frame? And finally, are you looking for a rookie or a veteran on the market? Do you want a supplier that deals with a multitude of different polymers and not just LSR? Or do you want a supplier who is very good at processing LSR and building molds and developing projects entirely? So just a few forms of advice as you're selecting. Lastly, I want to leave you with some advice as you're skimming through and researching more on LSR. Our website has a tremendous amount of data in the form of blogs, webinars, and case studies. Please take a look at our website and feel free to navigate around. If you have any questions, please use the Contact Us form, or you can email us directly, info@simtec-silicone.com. And lastly, I want to remind you is that we are here to coach you. Is there some sort of project that's coming down the road that you would like to discuss in detail? Is there a particular topic within LSR you want us to expand on, like designing with LSR or LSR with two-shot? And also, if there's anything specific that you wanted to develop or see that LSR could be applied to, sort of like a co-designing or R&D project, please feel free to reach out to us and we'll see how we can help. Thanks again for joining us today on today's webinar, and we hope to see you again in the near future. Have a good one.